So I've been asked to work problem 6.3, chapter 6, dealing with applying the valence bond theory to carbon dioxide. So I would say the first thing you need to do is take a look at Lewis dots. Hope that works. I'm going to bring up Lewis dot for oxygen and carbon. And once we do the whole Lewis dot procedure, we end up with a molecule that looks like this, where carbon is sharing its 8 electrons between the 2 oxygens, and we get rid of the dots that are bonding dots, and we see that we have a double bond here between each oxygen and the carbon. Now, the question that valence bond theory is going to pose is, what kind of orbits do we have going on here? Not orbits, what type of bonds do we have going on here? And can we determine which electrons and which suborbitals are making those bonds? And the answer is yes, we can do that. So I'm going to start by bringing up carbon, and I'm bringing up the electrons that are going to form those sigma bonds. Because remember, with your double bond, one of those bonds is a sigma bond, that head-to-head fist bump bond, and it's going to do that with each one of the oxygens. So those are the 2 sigma bonds. And then we have to drop in place the pi bonds. And there is one pi bond, and then there's the other pi bond. So now we have taken care of both double bonds. Oh, let's go ahead and label those pi as well. Okay, so we've taken care of the bonds between carbon and the 2 oxygens. Now, Lewis dot tells us that each one of these oxygens has has 2 pairs of non-bonding electrons. So I'm going to drop those in as well. And I have color-coded all of these to give you an idea that the things in purple are the orbits for oxygen's electrons, and the things that are kind of red are carbon, and then the things that are brown are the electrons that are shared between them. You get the idea. Hopefully, I'm doing this on the fly, so hopefully you get the idea. All right, so we've labeled the sigmas, we've labeled the pi's. Can we determine where these electrons are coming from? Well, yeah, we can. Let's start with carbon. The thing that we know about carbon is that in order for it to form 4 bonds, its 4 valence electrons have to undergo sp hybridization. So these electrons that it's sharing with these 2 oxygens in the pi bonds, the sigma bonds, are going to be sp hybrids for carbon, and the electrons that it's sharing in those pi bonds for carbon are also going to be sp hybrids. Now, what on earth is happening with oxygen? Well, let's just start with the easy business first. Let's look at some of these non-bonding electrons. Non-bonding electrons have a tendency to stay in an orbital that is high energy, and that's most likely going to be a p orbital. So we can say that this is going to be, I just lit one up, that for the oxygen on the right, we can say that the lighter purple orbital at the top is going to be the 2p in the x dimension orbital occupied by that lone pair, and that the lone pair at the bottom is going to be the 2p y orientation, and the one that's going to form the pi bond. Is it possible to have a double bond with an s suborbital? No. So the pi bond is going to be formed by the 2pz. Now, does the z and the x and the y matter? No, it doesn't really matter. But I'm just choosing this type of an orientation because I think it's just kind of gives you some labels and something to hang your hat on in terms of this is existing in 3 dimensions. And I'm just choosing the x, y, and z randomly to drop them in, to show you that your pi has to be as a result of a p orbital. And in the case of oxygen, it is just a regular p orbital. In the case of carbon, it is a hybridized sp orbital. And we can do the same thing for the oxygen on the other side, and we would come up with the same answer. I didn't label it. But that's how you would go about doing that. You look at what you have and just go through the process of thinking, who can form a double bond, who can form a single bond, and that sort of thing. So that's a little bit about the carbon dioxide question. Okay, so in this problem, we're being asked to apply valence bond theory to this triiodine ion. And with this one, I'm going to say, let's actually go through the steps of doing the Lewis dot, which means counting the electrons and then placing them where they're supposed to be. So let's bring up the Lewis dot for iodine. It is a halogen. It'll have 7 electrons in its valence shell. But we got 3 of these iodines. We have 3 of them. Each one is going to be bringing with it 7 electrons. So we're going to have 7 times 3 plus an extra electron because it's negatively charged. So we're going to have to place a total of 22 electrons around these 3 iodines. So before we do that, let me ask you this. What row does iodine live in? Well, iodine lives in the 5th row. And if you remember back to when we were talking about subshells and what row, if you are an element in the 5th row, you have the potential of having 5 subshells. You could have an S, you can have a P, you can have a D, you can have the mysterious F and G. So when we start thinking about things that go beyond the 3rd row or get into the 3rd row, what are we thinking about? We're thinking about the influence of having a D suborbital, that D shell, and an expanded octet. And I'm a little suspicious of this because when I see 22 electrons, it's not a number divisible by 8, which makes me think we're dealing with some sort of funny monkey business happening here. So let's start dropping in electrons around our 3 iodines. Okay, so I've color-coded them. The terminal to the left is green. The terminal iodine on the right is red. I hope you're not colorblind, anybody. And I have populated the terminal iodines, and I've dropped in 2 electrons showing the bond with the central iodine, which is colored blue. Now that gives me 16 electrons that have been placed. We still have to do another 6 to get it up to 22. So we're at 16 right now. Here is 17, 18. You see where we're going? 19, 20, and 21 and 22. So placing these around the central atom, which is that central iodine, we're now speculating that what we have here is an expanded octet around this iodine. So if we get rid of the 2 electrons that are forming each bond between the iodines, our molecule ends up looking like this. We have a lot of unbonded pairs of electrons on this one. So let's see if we can keep all this straight. Let's start looking at valence bond theory and bringing up the orbitals. So I'm going to bring up my central iodine first. I'm going to show this orbital right here, and it's going to bond with the iodine on the right, and it's going to bond with the iodine on the left. And we can pretty much guess, since we're looking at just a single bond, that these are going to be sigma bonds. Now we also have to find homes for all of these lone pair of electrons. So here on our iodine on the left, I've populated it with its 6 lone pair of electrons, and with the iodine on the right, I'm going to populate it with its 6 lone pair of electrons. And I'm going to have to do the same thing for the central iodine as well. So here are its 6 lone pair of electrons. That's kind of pretty. All right, so let's see. How can we determine where all of these electrons are living? Well, if we look at the terminal iodines, we can pretty much guess that its lone pairs of electrons are going to be occupying the higher energy p orbitals. So let's just drop that in, 5p, x, y, and z. And the same thing would be true for the green one, but I didn't do that animation. And what sort of electron orbital, I guess subshell, is going to form the terminal iodine's sigma bond? Probably going to be that lower energy S subshell. So that's how that's where these electrons are coming from to form the bonds, and where the lone pairs are living on the 2 terminal iodines. Now what about the central iodine? This is where the monkey business is happening. So what's happening here? Well, how many sets of electrons do we have to find homes for? How many pairs of electrons does this central iodine need to find homes for? Well, it's sharing a pair of electrons with the iodine on the right, so there's 1 set of electrons. It's sharing a set of electrons with the iodine on the left. There's a 2nd pair. And then it's got this lone pair down here at the bottom. There's 3 sets of electrons. And then we have the 2 sets up at the top. So this central iodine has to find homes for 5 sets of electrons. So what do you think is going to happen? Well, it's probably going to have to undergo some sort of hybridization in order to do this. It's the central atom that is going to undergo some sort of, in this scenario, and I say in this scenario because the terminal atoms aren't bonded with anything else. So it is the central atom that is going to have to undergo that reconfiguration of its orbitals in order to make this accommodation. So we know that we have the potential to draw from an s, p, d, f, and g. So we can pretty much guess that one of these orbitals is going to be the s orbital. We're probably going to recruit all 3 p's. So we've got 3 p's and 1 s. That gives us 4. We only need 1 more at this point, so we're going to recruit a d. So these are going to be the 5 orbitals that get hybridized to create this configuration for the central iodine to make homes for all of these electron pairs. So for the central iodine, the orbital that's creating that sigma bond is going to be an sp3d in both cases. And the 3 non-bonded pairs of electrons are also going to be occupying some version of an sp3d orbital. So that's that. Hopefully that adds clarity. All right. I think that's it.